Hello everyone. I'd like to talk about a practical application of the Cook-Levin theorem, which is our final project. So the Cook-Levin theorem says that any problem in NP can be reduced to SAT. That's one of the things in the Cook-Levin theorem. So there's lots of problems in NP that are pretty hard, and we don't really have necessarily other good strategies to solve them. And so what I'm going to have you do in this assignment is explore how we can use reductions to SAT to come up with a practical solution to solve really difficult problems that we might not otherwise know how to solve. So I'll walk you through in this tutorial how to do that for Hamiltonian cycle, which is one of my favorite NP-complete problems. So yeah, among other things, you can solve any problem in NP with a polynomial time reduction to SAT. So that means you can solve other NP-complete problems, which SAT itself is an NP-complete problem. So the first thing I want to do is show you the Python interface that I set up for CNF formulas. And so it's probably easiest to show you with an example. So I set up a little class here that allows you to add different clauses. And you can look at the documentation of that. But let me start off with a little example here. Let's say that this is the clause that I wanted to add here. And so what I'll do is I'll say, okay, CNF equals CNF. So the class is called capital C, capital N, capital F. And then I'll add each of these clauses. So I'll say cnf.add clause. And the way that you specify it is as a list of tuples. So the first element of the tuple is the name of the variable. And the second element of the tuple is whether it shows up as itself, in which case I'll say true. Or, as I'll see in the next example here, whether it shows up as with a not in front of it. So here I would say x1 false. And then there's one more element in the first clause there, which is x2, which shows up as itself. So I'll say true there. Going to add two more clauses here. So I'll fast forward through that for a second, but it's the same kind of thing. Oh, actually, sorry, three more clauses. There's one in the end that only has one element. All right, so now what I'm going to do is call the solve method to get a certificate. And so I'll say cnf.solve. And let's print that out and look at what that is. So when I run this down here in the terminal, so I'll say python cnf.py, what I get here is a certificate. So it tells me, okay, one satisfying assignment of this is if x0 is false, x2 is true, and x1 is true. So it doesn't come out in a particular order because it actually presents the certificate as a dictionary here, where the keys are the variables and the values are the assignments that make the formula true. So yeah, just checking this. In fact, there is a method to check this. If I would say cnf.isSatisfied that should print out true, and it does. If I were instead to make x0 true, so I changed my mind here and I said, okay, actually search of x0 is true, that's going to violate this clause up here, right? So the whole thing will be false. So if x0 is true, this clause is false, and then that's a false ANDed with other things, so that nullifies the entire clause. So now if I print is satisfied, it'll print false. Okay, so that was not the correct certificate, although cnf.solve will give the correct certificate. Okay, let's say that I happen to add a contradictory clause here. So if I were to say add clause x0 true. So that contradicts this clause here. You can't be both true and false for x0, so there's no way to satisfy that. If I run that here, what I get is the empty clause. So that's the convention that I follow here. Okay, but let's start to talk about the reductions now. So I'm going to walk you through how to reduce a Hamiltonian cycle to SAT. And so first, the definition of a Hamiltonian cycle is a permutation of vertices so that each adjacent pair of vertices, including the last and the first, is connected by an edge in the graph. And so here, this was an example I gave before when I made a video on Hamiltonian paths. The only difference with the Hamiltonian cycle is that I actually need to connect. Let me see, where can I actually connect these up here? Oh, I don't think I can easily connect this up in the graph. I'm going to have to find a new example. So a Hamiltonian cycle here could be, let's see, 0, 4, 4, 3, 3, 7, 7, 2, 2, 5, 5, 6, 6, 1, 1, 0. So I'm actually completing that loop. That's the difference. So still a permutation. So I'm visiting every vertex exactly once. But now I actually want to make sure that my first and last vertices are connected by edges that are in the graph. So I look at this, I was just highlighting here. See, I never took an edge that wasn't in the graph. Even if I delete that, you can see, So I'm not cheating here and using edges that aren't there. But, so let me, shoot, what happened to that? Okay, there we go. Okay, so before I get too much into the reduction, let me at least define some data structures that can handle storing this. And then I'll talk about the reduction. Okay, so jumping back in here, I created a new file called hamcycle.py. I imported the CNF stuff and I imported NumPy and Matplotlib because I'm going to do some plotting and some other utilities from there. So let me make a class called graph. And what I'll do is, in the constructor, I'm going to initialize a random graph. So initialize a random graph. And actually, so I'll pass along two parameters here. The first one is the number of vertices, or maybe I'll call it V to be consistent with what I'll write in my derivation later. So V is the number of vertices, and seed is the seed for randomness, and each seed will give a different graph. So we can repeat graphs if we think they're, if we're trying to debug and we think there might be a problem. So the first thing I'll say up here up front is np.random.seed0. So what I'll do here is I'm just going to store a set of edges. And I'll represent the edges as tuples of indices. So the first thing I'm going to do is generate a random permutation and add all the edges. So first I'll just make sure that there actually is a Hamiltonian cycle in the graph just by constructing a graph of only that Hamiltonian cycle. And then what I'll do is add some additional edges to make the problem harder. And I'll talk about that in a moment. Oops, okay. So let's do the random permutation first. So I'll say perm equals np.random.permutation v. And so what I'll do here is I'll say for I in range v, take out pair of indices in permutation. So I'll call the first one I1, and I'll call the second one I2. And here's where I do something a little fancy. I'll say I2 is I plus 1 mod v, because remember, I want to connect the last one to the first one. And so what that'll do is it'll loop around. If I am at index v minus 1, I plus 1 will be v, my v will be 0. So that loops me around to the beginning. And so now what I'll do is add this edge. And my convention is lower index goes first. So I won't duplicate the edges here. These are considered undirected edges that go from one to the other and back. But I'll just say I1, I2 is equal to min, I1, I2, max, I1, I2. So I1 is going to hold the smaller one, I2 is going to hold the bigger one. So I'll go ahead and say self.edges.add I1, I2. Okay, so now I want to add some additional edges. So first I'm going to figure out what edges are left. So what I'll do is I'll just loop through all possible pairs of vertices, keeping that convention that the first index is smaller than the second one. And so I'll say here edges left, that's going to be a set as well of tuples. And I'll say if this edge ij is not in self.edges, then I'll go ahead and add that to the edges left set. And now what I want to do is pick some edges in edges left to add. And this is where it gets a little interesting. So I want to add enough edges to make it a little hard to find the Hamiltonian cycle. but not too many so that it's trivial. So somehow there's like a sweet spot in here, and this is something I'll have you think about on your own problem when you initialize random problems. But if there's too few things, there's too few clauses, it's kind of easy because there's not that many clauses to check, and I mean, if you just look at it, you could almost brute force it. But if there's too many edges, it's kind of the same thing. For a Hamiltonian cycle, there's just so many different ways to choose one then. I mean, if you were in the complete graph, you could choose every single possible permutation. So in other words, if all the edges were there, there's there's n factorial solutions to this up to a cycle. So that's too easy as well. So we kind of want something in the middle. And so what I'll say here is the number of edges, I'll make that be something like the number of vertices to the, I don't know, I'll say maybe 5/4 power or something. so this is not, if it were all pairs of vertices, it'd be v times v minus 1/2. But this is not that. So actually, but let me make sure that, just as a sanity check, I'll make sure this is not exceeding the maximum it could possibly be. So that's the most that's the most edges you could possibly have. Let me make sure I don't accidentally exceed that for some reason. I don't think I will, but and so now what I'll do is I will see what's left. I'll say for I in a range E minus length, or E minus V, right? So I've already added V edges, and so now I'm going to take some that are left. Actually, what I'll say is for I in mp.random.permutation E minus V. So this is the total number of edges I want to have. I've already added V for the Hamiltonian cycle. And let's add the ones that are left from this edge set here. And so I will say this is the permutations, making sure that they're unique here. Oh, actually, I guess I should say permutation len edges left from 0 to E minus V. That'll do it. So I'm going to take a permutation of the indices of everything that's left. I'll just take the first E minus V of those, so it'll shuffle them and just take the first E minus V of what's left, and then I'll add each of these. So now I'll say self.edges.add edges left at index I. Okay, so I think that is my random initialization of a graph here. Oh, and I'm noticing here Visual Studio Code is telling me I didn't use my seed variable, so I should actually not always seed it with the same thing. I'll seed it with that, the seed that I passed along. Okay, so the last thing I want to do here before I go back and talk about the reduction is let me just make something to plot this. That would be very helpful. So I'll make a method to plot this. I'll make it so that you can pass along a certificate, which in this case is a permutation. So search is list of the indices. So this is the permutation certificate of the Hamiltonian cycle. But by default, I'll make it empty. So you can just plot the graph by itself. But if you want to, you can plot the certificate. So to plot the graph, first I'll come up with locations of the vertices. And so actually I should save that V away here so I can access it as an instance variable elsewhere. So I'll pick that V back up here. And I'll say, let me make the x coordinates. Actually, what I'll do is I'll arrange these vertices along the circle. I mean, there's a bunch of different ways to draw graphs, but a simple way is to just arrange the vertices along the circle. So what I'll do is I say theta is linspace 0 to pi v plus 1 from 0 to v. That will evenly space samples around the circle. If I then make the x coordinate be cosine of theta, and the y coordinate be sine of theta. So what I'll do is I'll scatter these vertices. I'll make sure they're up front, so I'll say, I'll make them kind of big here. That's the size. I'll say z order equals 100. That puts them out front. And now what I'll do is draw each edge. So I'll say for I, j in self.edges. I'll pull out the first, or actually all I got to do is say plt.plot xi, xj, so going from the x coordinates of the first vertex to the x coordinates of the second vertex, and then yi, yj. Y coordinate of the first vertex, y coordinate of the second vertex. I will color this black. I'll make it a little bit bigger because what I'll do is I'll draw the certificate on top of this. So I'll say line width maybe equals 4 or something. I don't know. Let's see how that looks. So if I were to go ahead and instantiate a graph object down here, and I'll seed it with 0, and then we're going to go say g.draw, and then plt.show. Let's see if that works. It's missing a positional argument seed. Oh, because I'm supposed to give it the number of vertices I have. So let's say I want one with 10 vertices. It says set object is not subscriptable. So what I should have done here is I made edges left a set. I should just made that a list, actually. So that should be better. But it'll be nice for me to look up edges quickly in a set, so I think I don't know, I may or may not need this to be a set, the edges, but I'll just keep it as that for now. Graph object has no attribute draw. Because I called it plot, I should call it draw. Okay. Finally, here we go. So there's a graph. I don't know, so I put a lot of edges here. Let me actually say how many edges that I put there. Maybe it's too many. So if I print this out, maybe as a percentage. So I'll say this percent edges. And that would be 100 times E over V times V minus 1 over 2. So let's see. It's telling me here I took, okay, about 38% of the edges. Let me make this a little bit smaller. Maybe I'll say V to the 10/9 or something. So you see I took a little bit fewer edges here. I don't really know what the sweet spot is. Maybe I'll go back and I'll just stick with this. But yeah, but just to show you, because of the seed, every time I get the exact same graph. So notice that number 37.778. Well, I guess that'll be the same, but just notice the way that the graph looks here. It's the same every time. But as soon as I change the seed, it'll change a little bit. So notice that that's a different graph now, but if I keep running it with seed of 1, that'll be the same different graph. All right, so we got the graph class set up now. And we can talk about now how to go back and do the reduction to SAT, so we can actually solve for the Hamiltonian cycle. Okay, so in a reduction to SAT, what we have to do is come up with a bunch of variables and a bunch of clauses that enforce constraints on those variables. So the variables we're going to choose are going to be indicator variables of which indices we choose which vertices. So there's going to be v squared variables, which is why I've drawn this table down here. And so this table I'm going to use to depict the variables here. And along the rows, I'll say this is the index in the permutation, right? So I have, in this case, 8 vertices, and I need to choose 8 of them in a permutation in some particular order. So along the rows, I'll have the index of the permutation. Along the columns, I'll have the index into the graph. And so I will have a variable for each index in the permutation for each index in the graph. So there will be v squared variables. And I'm going to make that variable a 1 if that particular vertex in the graph showed up at this particular index in the permutation. Now with the Hamiltonian cycle, we can cyclically permute the permutation, which means we can start anywhere inside of it. There are actually v different permutations I can write down that are all equivalent. But let me start this one, I don't know, let's say I'll start this one at 4 and I'll go counterclockwise. Yeah, actually I guess clockwise versus counterclockwise doesn't matter either. But I'll start at 4 and go counterclockwise here. So I'll say 4, 3, 7, 2, 5, 6, 1, 0, and then I repeat the 4. So that is the certificate for the Hamiltonian cycle. And what I want to do is convert that into a certificate in a SAT reduction here. And so what I'm seeing here is okay, 4, index 4, vertex, is chosen as the first index in the permutation. So that's going to be a 1, that variable. So I'll call them xij. So that variable x04 is going to be a 1. So xij is true if vertex j is chosen at index I in the permutation. Okay, so 4 was chosen at index 0. 3 was chosen at index 1. So I'll put a 1 there. 7 was chosen at index 2. 2 was chosen at index 3. 5 was chosen at index 4. 6 was chosen at index 5. 1 was chosen at index 6. And 0 was chosen at index 7. So those are all of the variables that will end up being 1. And all the other variables are 0. So I'm not going to write out all the zeros here. This is what's referred to as a sparse matrix. Most of the variables are going to end up being 0 in a certificate in the reduction here. Okay, so now that I've established the variables for the reduction of SAT, I need to somehow implement the verifier for the Hamiltonian cycle in the language of SAT, so using SAT clauses. That's what the Cook-Levin theorem really does at the heart of the proof. It says, I'm going to choose some constraints in CNF form that enforce the things that my verifier does. And so here, there's two things that a verifier would do for a Hamiltonian cycle. So the first thing is enforce being a permutation. So I want to make sure that whatever I choose here is a permutation. In the language of this matrix here, what that means is it needs to be a so-called doubly stochastic matrix. What it means is each row and each column need to have exactly 1, 1. What that boils down to in terms of constraints is I'm actually going to have to say it that each row has at most 1, 1. Each column has at most 1, 1. And then finally, it's sufficient to say, actually, somebody pointed out in class, this is very, I was very impressed when they realized this, that actually it's sufficient at this point. You could say, you want each row to have at least 1, 1 as well. So here I'd say at least 1, 1. So if you have at most 1, 1 and at least 1, 1, then you have exactly 1, 1. And it turns out we don't need to say that for the column. That would be redundant. So these three constraints together make sure that this is a so-called doubly stochastic matrix, that it has exactly 1, 1 in each row and each column. Pick out any row here, I only see a single 1 there. I see exactly 1, 1 there. Pick out any column, I see exactly 1, 1. The other constraint is that we need to be choosing edges in the graph. So just a permutation by itself is not going to be particularly useful in the context of Hamiltonian cycle. This is just going to give me back n factorial permutations, but I need to choose specialize those permutations to actually choosing edges in the graph. So let me try to knock these out one by one here. So saying that each row has at most 1, 1. Well, that's like saying, okay, let's suppose that I pick, so I'll refer to my variables here. Let's say that I pick x at row I, column j. And I'm going to use array indices here. I know I just said xij there before, but array indices, it'll be a little bit nicer as I move through. So let's say that here's a variable that I chose to make it 1. So the 1 at row I, column j. Well, that means that I better not make this at any other column be a 1. So in that row I better make sure that if j is the one that I choose, then for all k not equal to j, those ones better be a 0. Okay, but this is not the way that we write something in CNF form. So what I have to do actually is convert this into a clause that's an or. And the way that I would do that is to say not xij or not xik. So what you do is you take the premise and you knot it, and then you put what's supposed to follow. And the reason this works is because if the premise is false, I don't care about this implication. And so the whole thing should drop out. So if the premise is false, then not premise is true, and that automatically satisfies this whole clause. Another way to look at that is to say, if everyone in theory of computation is a billionaire, then I'm president of the United States. Well, the premise is false, and so that is fine for me to say, anything goes. Basically, the whole implication becomes irrelevant. So I don't really care what's on this side. It doesn't have to be true. But if the premise is true, I better make sure to enforce that. So this is the way that we do that conversion there. It's a common trick. So oftentimes you want to write those premises. But what I want to do now is look at, I need to AND all of these together. And so I know that this is something I'm going to have to do for every k not equal to j. But also, this is something I have to do for every element in the table. So over all ij. And so this is actually going to turn into the AND of a bunch of little two-element OR clauses here. So I have over all I over all j. For all k not equal to j, I have a clause of this form. And so that, that's kind of a lot of clauses. I mean, so this is going to be big O of v cubed clauses here that this accounts for. That's a lot. But actually, so practically it might not be so great, but in terms of what the Cook-Levin theorem guarantees, it's perfectly valid. We're just trying to make sure that we have a polynomial time reduction. And so we have big O of v squared variables, that's polynomial time variables, and we have big O of v cubed clauses in this section, and that's also perfectly polynomial. We might not like the polynomial, but it's still polynomial. Okay. So that's fine. Now I'm going to do some copy and pasting because the other one is very similar. For each column having at most 1, 1, then it's just like saying, okay, I'm in column J, row I. I want to make sure that that row K, column J, is false. And so in this case, I need K to not equal I. So let's just double check that for a second. If let's say that I'm in column 1 here, so J is equal to 1, and I chose my I to be 6, then I'm going to make sure that that K equal to 5, or K equal to 4, 3, 2, 1, 0, or 7 can't be true in that column J. And so, yeah, I just have to tweak this down here. I have to say K not equal to I. And then I'm going to say not ij implies not kj. So just switching around the indices a little bit here. But very similar idea, and still big O of v cubed clauses there. All right. And then the last one is actually a little bit easier. Each row having at least 1, 1. Well, that's just going to be one humongous OR clause. So for example, I would say, for row 0 to be x 0, 0, or x 0, 1, or ... x 0 v minus 1. So I need to make sure at least one of these are true. So I can do that by putting them all into an OR clause. And I'm just going to make sure I do that over every row. So for every row, I want to make sure that at least one element is true. That can be expressed with an OR clause. And that is going to use big O of v squared this time, because each clause has v elements and there are v such clauses. Okay, so that's what we have for enforcing being a permutation. Choosing edges in the graph is actually a bit interesting. It makes a little bit more sense to consider. Let's suppose ij is not an edge in the graph. So ij, so two vertices indexed I and j, we're saying there's not an edge between them. Then what we would say is, okay, we better make sure that if we choose, let's say at row k, let's say that we happen to choose vertex I. Well, then we better not choose vertex j at row k plus 1. So here, it's like saying, okay, I chose at row index 1, so k is equal to 1. I chose vertex 3. Then I better not choose vertex 1 in the next row, right? Because there's no edge between 3 and 1. So if I go to row 2, k plus 1, this element cannot be a 1. If I've chosen a 1 here, this element cannot be a 1 because that edge is not in the graph. Now there's one little tweak I need to make to this because this is a Hamiltonian cycle. We actually loop around. So if I were in row 7 here, so row 7 I chose a 0, then that means actually if I have to go back up to the first row here. So I'm in row 7, chose a 0. That means that in row 0, I can't have chosen, for example, a 5. There's no edge between 0 and 5. So I chose a 0 on 7. That means that this has to be a 0. And so to make me circle around, I'm just going to say, okay, the next row is actually k plus 1 mod v. So that'll cycle me around. Normally it's just the very next row index, but sometimes, if I'm in the very last row, it'll cycle me around. That's the row that I want to look at and make sure that I'm not accidentally choosing a vertex that would violate an edge in the graph. So I'm going to use the same kind of trick here, and I'm going to convert this to CNF form by saying not xik, or sorry, not xki, or not x k plus 1 mod v j. And that is going to be over all ij not in the graph. So I'll just write that here. I'll say over all ij not in graph. And it's also going to be for each row. So this is something I have to worry about in every row. So let me say that's also ending over all. So I'm going to have one of these clauses for each row, for each edge that's not in the graph. And so once again, you see here, this is going to be a cubic number of clauses. But once again, we're completely fine with that because we're just looking for a polynomial time guarantee, and this is polynomial time. So we're totally in line with the Cook-Levin theorem here. All right, so we got all of our clauses. And so now what we can do is jump back into the code. So what I'll do is I'll put all the clauses over here. And what I'll do is implement these in code here. So one thing I want you to do is I want you to make a method in your own class when you do this in the final project. Make a method called getCNF formula. So I'm back in my ham cycle.py here. And so I'll initialize or instantiate a CNF formula object. And what I'll do is I have some helper methods. So I'll make one called get at most 1. And what this is going to do is fill in the constraints, the constraint clauses that enforce at most 1, 1 in rows and columns. And so what I can do is, okay, let me get this my number of vertices, which I've saved as an instance variable here. So this is going to be a triply nested loop. I can actually implement it as such here. So I say for I in range v, for j in range v, for k in range v. And so for this first one, I'm going to say if k is not equal to j, then I'm going to add this clause here. And so actually the way that I've set this up is a clause, so it consists of a tuple of something that's hashable and a boolean. Well, what's hashable can actually be a tuple. In the example I showed before, I made it a string, right? So the variable was a string. But I can make my variables be tuples because tuples are immutable and they're hashable, as long as they have hashable things inside of them. So what I can say is cnf.add add clause, yes, clause. And so my first clause is going to be ij, and that's going to come in as false. So notice I can make my variable actually be a tuple here. So I set that up for you for convenience. And then the second element of my clause is going to be ik. I want that to be false. All right, so again, just to tell you, the clauses are made up of elements. The variables can actually be tuples. So that's a variable in my CNF clause. Now I'm going to do something awfully similar for, so this is each row has at most 1, 1. But then I also want to do each column has at most 1, 1. And so there I'm saying if k is not equal to I, then CNF.I clause not ij, and then in this case it's not kj. Okay, so this is, so that should be good for the get at most 1, 1. So I'll just call that helper method here, and it'll fill in those clauses. Actually, before I go too much further here, let me just see what I've done so far. Make sure that it runs and look at what it looks like. So if I were to just return this straight up and then print g.get CNF formula, let's pop into the terminal here and run this. And actually, I don't need to see the plot because the graph is not really relevant yet. These are just the permutation constraints. But if I were to say Python hem cycle, I see a bunch of clauses, of course, because there's a cubic number, right? This is a graph with 10 vertices. So just looking at a few of them, I see, okay, you know, if I'm at 0, 0, I better not also be a 0, 1. That makes sense, right? Let's just spot check a couple more. If I'm at a 2, 6, I better not be at an 8, 6. So that's one of the column constraints there. So I'm saying, okay, if you chose row 2 for column 6, you better not be in row 8 also at column 6. Okay, so that's looking pretty good. So you know, you can always use, I've implemented this repr, this toString here, so you can always print out your CNF clauses and make sure that they look right. And I would definitely check them as you're going. All right, cool. So that's fun. Let me do this one now. So I've taken care of the row and column, and hopefully we're convinced of that after looking at that. Let's do at least 1, 1 now. So I will say here def get at least 1, 1. And so that's just a matter of saying, okay, let me go through I in range v, and then, okay, in this case I'm gonna have a clause that I'll fill in. I'll say for j in range v. I want to make sure that, so I look at this here, I'm trying to space things out a little bit because, you know, I made it as clean as I can, but it's still a little bit messy. So I'm going to say, okay, row I, column j. I want at least 1 column for each row to be true. Okay, so it should be as simple as that. So just write in the comments here. This is going to enforce at least 1, 1 in each row. And of course, I'm noticing here that CNF was not used. I need to make sure that after I've done that hard work of creating the clause, I want to add that clause to. All right, so that's great. And now I'll just go ahead and say self.get at least 1, 1 CNF. So I call that helper method down here. So the last one I got to do is actually enforce the edges in the graph. And so that's where I have my double negative. I say I don't want to add an edge that's not in the graph. So let me go through and try to do these now. So first I'll make a set of edges called not edges. And so what I'll do is, and this is where it's really helpful that the edges were set before. I remember I was kind of waffling about that. I said, I think it's a good idea for these to be a set. I had them in the back of my mind. It's going to make this step a little more efficient. So what I'll do is I'll look through all potential edges. So I'll loop through all vertices, and then I'll loop through all other vertices. And I'll say if not ij in self.edges. Then I will add not edges. I will add ij to that. So it's just having edges be a set makes this an efficient operation. I can check, you know, it's some kind of hash table in the background. I can just find out very quickly whether this edge is actually in my edge set. So now I have all my ij's that are not in the graph. And so what I can do is just loop through. So I'll say for k in range v. So over all rows, I want to look at, and this is what I love about Python. If the code is so close to what I wrote down here already. So I'll say for ij and not edges. Then I will say, okay, here's the clause I want to add. I want to say cnf.add clause. First element's going to be ki. There we go. Ki. That's going to come in as false. And then the second element is going to be k plus 1 mod v. And let me make sure, this is really, the parentheses are kind of a nightmare here. So this is, okay, this is the second element in the clause. The variable is actually a tuple, whose first element is k plus 1 mod v, whose second element is j, if I'm looking there. And that also comes in as false. And this is part of a big list. So these two elements here are actually in a list. Okay, I think I got that. It's a little bit ugly there with the parentheses. But otherwise, it's not too far off from what I wrote down here. Okay, so first element, not kij. Second element, not quantity k plus 1 mod vj. Okay, I think that was it. So I'll say self.enforce edges cnf. So yeah, let's go ahead and run this and pop open a terminal and see how it does. So I look at this and I see, okay, cool. Clearly I'm getting something that is new here. I'm going from row 9 to row 0. So that's actually one of the ones that loops around, right? And it's saying if you choose a 2, you better not choose a 3 right next to that. So it might be nice to actually look at the graph and see what's up with that. Actually, I better go ahead and number these vertices here. So let me go back to my draw method. And right after I scatter these, I will number them. I'll say plt.text x, I, y, I. And then I'll say I will draw a little I there. So I do that. It's a bit annoying. Those numbers are kind of covered up by the dots. So let me just offset them a little bit. So I will say maybe x plus 0.05. Okay, that helps. So I look at this here, and it told me I wasn't supposed to add an edge between 2 and 3. And I see there's no edge between 2 and 3. Awesome. Let me just spot check another one. So it says you shouldn't add an edge between between 9 and 0. And yeah, I don't have an edge between 9 and 0. Okay, awesome. So I think this is working. What I need to do now, though, is implement a solve method. And so the first thing I'll do is get the CNF formula. But then I want to actually solve it. And so here, actually in this case, I'm going to go down to a smaller graph. I'll show you why in a second. But if I were to say cnf.solve, so I'll say my search that I get back is equal to cnf.solve. Let's just see if that runs. And so I'll say g.solve here. Go back to my terminal. Okay, it solved it. This is a much smaller graph. It's using almost all the edges. But it solved it, and then I got my cert back. And so from that cert, I can read off the solution. So one thing I have to do is translate the SAT solution back to my language. So I'm going to go through this cert. So I'll say for, so this is ij, and then the value that it gets. I'll say insert.items. Just for those who are a little bit rustier on dictionaries, let me show you what that does. So if I were just to run this method, okay, it takes a second, and then yeah, so this is unpacking the search in this way. So I take out the row and the column that, you know, really the variable, but I'm unpacking that variable into the row and column of the tuple it was, and then seeing whether it was true or false. Now, if it was true, that means it was chosen. So I'll say if val, then what I'll do is I'll have some permutation that'll fill in. So say, you know, permutation is 0 times self.v. If this is true, then it says, okay, the index I of the permutation, I chose vertex j. And so that's how I get my solution there. And so what I'll do is, okay, so supposedly this is a Hamiltonian cycle. What I should do then is draw it. Let me draw it. So I'll add, remember I had this thing here, search, or I guess I'll call it perm here. I had this thing that I could pass along to draw. So I'll say draw the search certificate permutation. So we can actually check our solution here. So in this case, I'll say for I in range, or maybe it's a different. I'll say for k in range, length of permutation. I'll say I1 equals k, I2 equals k plus 1 mod v. Because this permutation, I understand, is actually a cyclic thing. And so then what I'll do is I'll just plot this here. I'll say this is x, I1, or yeah, I'll just say I and j so I can reuse that code. So that's index I into my thing. Let me draw this as an orange line, and I will draw it as a dotted line so I can see if it's on top of something that's already there. Okay, and so now what I'll do is when the solution is finished, I'll return the solution, and I will draw the solution. So let's see how that goes. Okay, now something is off here because this shouldn't. Okay, so the part of when I did this, you know, I made sure I drew dotted lines so you can see if there were actually edges in the graph. Somehow it chose an edge from 2 to 4. So there's a bug somewhere, either in the way that I made my clauses or in the way that I'm unpacking this here. Okay, I look back and I realize there's actually 2 mistakes that I made. The first mistake is these edges are undirected. So when I add my clauses constraining them, I need to actually add both directions, ij and ji. The order that I go through them doesn't matter. It doesn't matter if I visit I first or j first. The other mistake I made was just with plotting. This is kind of a trivial mistake, but I want to make sure I'm actually referring to the vertex index, not the permutation index. So let's try to run this now. Okay, so that's a Hamiltonian cycle. That looks good. So one thing I want to mention though now is that's all well and good. Let's try just going up one vertex. No, let's go to 6 vertices. Now it's taking a really long time, and unfortunately this is the one downside of switching from Java to Python. So the last time that I ran this assignment, I did it in Java and I implemented the DPLL solver in Java. The whole thing was pretty much self-contained. But in Python, it's a little bit too slow to scale up. And so what I've done here is I actually wrapped around a library called Glucose, or a technique called Glucose for doing sat solver. I mean, sat solving has been around for a long time. People have done a really good job making fast sat solvers. And so I made a wrapper around this other library that we'll set up in class. It should be very simple to install. You should just have to write pip install PySat, I believe it's called, PySat. Or was it PySat? Or maybe not, because no, it wasn't. It's actually pip install Python sat. Okay, my bad. PySat is something different. I don't know what I just installed. Okay, it's actually Python-sat. So I'll just write that here. Pip install Python-sat to use this. But so if I switch, okay, it's a little bit sad for me because I worked very hard on my own solver here. But this will make us be able to solve much more exciting problems. So if I were instead say solve glucose, it'll be able to actually solve this. So let's go back up and run that again. Oh no, sorry, not solve glucose. What was it called? No, it was called solve glucose. Oh no. Okay, it's because I have to call this up here. It's when I'm solving the SAT problem that I need to do this. Okay, cool. So it had no problem with that. And look, nice. That's a nice Hamiltonian cycle on 7 vertices there. Now we can really scale this up. So let me go up to like 40. Glucose can handle that. So this is interesting. Only about 12% of the edges. Now I looked at this behind the scenes, and okay, so there's a monster Hamiltonian cycle there. It's hard to even really see what's going on, but glucose had no problem with that. In fact, if I were to time things here, the dominant cost was actually for me setting up the clauses. Glucose was able to just rip through them. But anyway, so that's kind of it end to end. Actually, there is, though, one more thing I want to do, and then I'll have you do on the assignment. As a sanity check, I want you to implement a method called check_cert that actually checks in my language a certificate. Now, look, I mean, the certificate we get back, if the reduction has been done properly, literally we are finding the certificate for this problem. But it was in the language of SAT, and so we did have to translate it back into this language. And so just to make sure everything is fully consistent, this is really just as a consistency check to make sure that everything is working properly. I mean, I visually inspected some of them to make sure they were right, but it's a little bit more difficult maybe to visually inspect this one. So it's helpful if I check the cert in the original language. So what I'll do, so in other words, in this case, make sure that perm is actually a valid Hamiltonian cycle. So the first thing I need to do is check that it's permutation. So maybe I'll say, okay, you're innocent until proven guilty. So you did well, or so it is valid. We'll start off by saying, okay, you did well, but let's check. Trust but verify. So if I say, a quick way to do this would be to say, if length of np.unique perm equals lang perm. So this is numpy.unique will just give me a list of all the unique elements in here. They're supposed to all be unique because it's a permutation. So, but I guess I'll say if they're not the same, then is valid is false. And then of course the second thing I need to check. I mean, it's almost like I'm really repeating the work that I did to express the verifier in SAT, right? So I'm literally redoing the work just in my own language. So hopefully you see that this is exactly the same as what I did for SAT. But yeah, so first one I check it's a permutation. The second one I check that there are edges in the graph. And so I'll just say, okay, let's look at each index here. So for I in range length permutation, or maybe let's say for k in range length permutation, I is equal to permutation index k, j is equal to permutation at index k plus 1 mod length permutation. And I'll just say is valid equals is valid, and I better make sure that ij, either ij or ji. That was the thing I screwed up a second ago. So ij is in self-edges, or ji's and self-dead edges. So just getting my, again, all my parentheses right here. So I have to at least have ij be in the edges or ji be in the edges for every pair of indices in the permutation. All right, so let's go ahead and see, was it right? If I then say print g dot check search perm. So we're going to wait a second, it's going to solve it again. And true, that's encouraging. So it probably should run a more extensive battery of tests. But yeah, that's it, that's end-to-end. So that's, you know, you're going to do something just like this for another problem. And see, that's the whole final project. And with comments, it was not even 150 lines of code, right? So I hope that this is fun. I hope that it opens your eyes to one strategy we might use to solve really hard problems. And I hope you have fun with this. So let me know if you have any questions, and hopefully this video helps.